Hello, my name is Surendra Gantiala. I'm a third-year PhD student at Cornell, and I'll be presenting our paper, The More the Merrier, on total coding and lattice problems and the complexity of finding multi-collisions. This is joint work with Huck Bennett and my advisor, Noah Stevens-Davidowitz. Theoretical computer scientists are generally interested in decision problems. I give you a string and you tell me whether it belongs to a language, which is some subset of 0, 1 star. But in this work, we're going to be concerned with function problems. As an example, and one that we'll come back to, consider weak pigeon. I give you a circuit which has an n-bit input and an n-1 bit output, and you output for me distinct x1, x2, such that c of x1 equals c of x2, a collision for this circuit. This is not a decision problem in that I don't want you to output a yes-no answer. I actually want x1 and x2. So how do we formalize this? Well, we're going to think of function problems as binary relations, where the first part represents the input and the second part represents a valid answer. So for weak pigeon, the first part would be a circuit, and the second part would be x1, x2, which form a collision. We're going to be interested in total function problems. These are problems where for every input, there exists a solution. More formally, for every x in 0, 1 star, there exists a y such that xy is in the relation. Notice that weak pigeon is total. There are 2 to the n inputs to the circuit and 2 to the n-1 outputs of the circuit. And by the pigeonhole principle, that means that 2 inputs must map to the same output. So a collision x1, x2 has to exist. And finally, we're going to be interested in total function problems which are in NP, TFNP problems. These are total function problems where there exists a polynomial time verifier which can verify answers to the problem for us. Notice again that weak pigeon fits this condition. Given x1, x2, which is a supposed collision, I can simply run the circuit on x1 and x2 and verify if it's indeed a collision. So what are some examples of TFNP problems? Well, proofs that certain objects exist correspond naturally to total search problems. The pigeonhole principle tells us that in a compressing function, a collision exists. That means that we can define a computational problem which is total, which asks us to find that collision. There are other such principles, and it's natural and fruitful to consider the complexity of the associated total search problems. It's interesting in its own right, but it also brings these existential proofs, which at first don't seem computational, into the landscape of complexity theory. So what are some other examples? Well, let's look at the TFNP hierarchy. At the top here, we have TFNP. Below it, we have some TFNP subclasses. PPP is the subclass of TFNP of problems which can be proven total by the pigeonhole principle. So for example, weak pigeon belongs to PPP. Similarly, PLS is the class of problems where totality can be proven using a potential function argument. PPA is the class of problems where totality can be proven using the handshake lemma. For example, Nash equilibrium is in PPA. So proofs of existence correspond to natural classes of total search problems. But there's a gap here. There's a class of very natural problems which somehow have yet to be classified in the TFNP hierarchy. And to tell you exactly what those problems are, we're going to take a short detour to coding theory. A code, which is a subset of q to the n, is just a set of points, which we're going to call code words, where every code word consists of a tuple with n entries, where each entry comes from the integers 1 through q. And we're going to say that the code has q to the k points. Here's a visual representation. The ambient space here is q to the n, and these blue dots represent code words. One of the most important properties of a code is its distance. The distance of a code is defined as the minimum Hamming distance between any two code words in the code. Here, these code words, blue points, connected by this green line, are the closest together, and therefore the distance d is the distance between these code words. And there are two properties of a code which kind of counterbalance. The first is the rate, r, which is k divided by n. This tells us how densely packed the code is. Notice that as k goes up, we have more and more code words in the code. So as k goes up, we should have the rate or the density of the code go up. The other property is the relative distance, which is just d divided by n. Notice that when r gets higher, d should get lower, because a more densely packed code cannot have code words which are as far spread apart. And in fact, there are known bounds for exactly how large the distance of a code can be. And we're going to use these to think about computational analogs. As an example, the singleton bound tells us that the distance of a code is upper bounded by n minus k plus 1. We can then define a computational analog of the singleton bound, which we're going to call singleton in all caps, where I give you a circuit which has a k-bit input and an n-bit output, and you give me back x1, x2, which are distinct, such that c of x1 and c of x2 are within n minus k plus 1 Hamming distance of each other. But what exactly does this have to do with the code? Well, let's interpret the image of C as the code. The input tells us which code word we're going to get, and the output actually tells us that code word. There are 2 to the k inputs, so there are going to be 2 to the k code words, and there is an n-bit output, so each code word is going to have length n. When viewed like this, it becomes obvious that there should exist x1, x2, 2 code words, such that the distance between c of x1 and c of x2 is at most n minus k plus 1 in the Hamming metric, which follows by the singleton bound. Therefore, we've used the singleton bound to show the totality of the singleton problem. Not only can you show its total, you can actually show that it reduces to weak pigeon. If you can find a collision, you can find 2 code words that are close to each other. But there are other bounds out there. We can expand this theory. For example, there's the Hamming bound, there's the Elias-Basso-Iago bound, and the MRRW bound. The Hamming bound we show is in fact in PWPP. It reduces to the weak pigeon problem. But these other bounds, they seem to require a stronger argument. So we're going to define a new complexity class and a new complete problem to capture these bounds. We're going to call this AB pigeon L, and it's going to be a generalization of a complexity class already defined in KNY18. I'm going to give you a circuit which has as input integers from 1 to A, and as output integers from 1 to B, and you should output distinct x1 through xl such that x1 through xl form an L-wise collision in C. And notice that this problem is total when the ceiling of A divided by B is at least L. This follows from the generalized pigeonhole principle. And for this problem, we can also define a complexity class. AB PMPPL is the set of all TFNP problems which are Karp reducible to AB pigeon L. AB pigeon L is therefore a complete problem for this complexity class that we're defining. We'll sometimes leave off the A and B when the parameters get rather complex and just think about PMPPL. So here's some of our contributions. The first part. We can show that the coding theory problems like singleton or finding 2 code words which are within the Hamming bound of each other correspond to weak pigeon. We can reduce them to weak pigeon. And the same for some lattice problems, which I'll introduce later. Furthermore, we can show that finding even closer code words corresponds to finding more collisions. It reduces to PMPPL for L equal to 3, 4, 5, and so on. And the same applies for lattice vectors. As you find more collisions in a compressing function, you can find shorter and shorter lattice vectors. And hence the name of the paper, the more the merrier. So let me give you a way to visualize all these problems. Here is on a grid where on the left we have R, the rate of the code, and on the x-axis we have delta, the relative distance of the code. And each point on this grid defines a set of coding problems. Each point R delta corresponds to a short distances problem SDP, where I give you an implicitly represented code with rate R, and I ask you to find x1, x2 such that the code words C of x1, C of x2 are within distance delta n of each other. In particular, for this point, since it has R equals 0.6 and delta equals 0.3, I'm asking you to find two code words which are within distance 0.3 n of each other, delta n, in a circuit which has an input of n divided by 0.6 and an output of n. So how hard are these problems exactly? Well, everything on this grid colored in red corresponds to an SDP problem, which is PWPP hard. What does that mean? That means that every point on this grid corresponds to a problem which is believed to be intractable. So therefore, the short distances problem everywhere here should probably be intractable. Okay, we know it's hard. What can we say about inclusions? Well, everything you see in this blue region here reduces to finding a two-wise collision in a compressing function. Furthermore, everything in this green region, which is a superset of the blue region because the green dots cover the blue region, corresponds to finding a 2n-wise collision in a compressing hash function, more collisions. But more interestingly, there's a smooth interpolation between the blue and green region as we increase k. What this means is the more collisions you can find in a compressing function, the better you can solve this SDP coding problem. For those of you who are familiar with the Elias-Basso-Yagov bound, this basically follows by unwrapping the proof of that bound and looking at the corresponding parameter regime. Now let's talk about lattices. I'm going to show that finding more collisions leads to solving lattice problems better, but to do that, we first need to define lattices. A lattice, specified by a basis, which is an n by n matrix, is all integer linear combinations of the basis vectors of that matrix. So for example, here's a visual representation of lattice. The red arrows correspond to basis vectors, and the red dots correspond to lattice vectors. We see that every red dot can be written as the integer linear combination of the red arrows, and is therefore a lattice vector. And this lattice should actually extend out all the way to infinity and is periodic. So what's the computational problem here? Well, we're going to be interested in the shortest vector problem. Well, for us, it's going to be the short vector problem, really. I'm going to give you a matrix A, and I want a short non-zero vector in the lattice specified by A. And if we want to base post-quantum cryptography off of lattices, which we do, we should believe that the SVP problem is hard. So what exactly do we mean by short or small vector here? Well, one way to think of it is a vector meeting Minkowski's bound. Minkowski's bound tells us that for a basis A, there exists a relatively short lattice vector in the lattice generated by A. The actual length of this doesn't matter so much, but just know that there is a bound and it's a relatively short lattice vector. So what's the computational problem? Well, we just write these words in red here, given and find. So I give you a basis and find me a short vector which meets Minkowski's bound. So we've defined the computational problem. What exactly is the complexity of this problem? Well, we can show that Minkowski reduces to pigeon. It reduces to finding a collision in a compressing function. This was already known before, but it was only known for the L-infinity norm. We are able to show it for all LP norms where P is an integer. But we can do even better than that. There's a better bound called Blichfeld's bound, which says that I can find a lattice vector in a lattice which is shorter than Minkowski's bound by a factor of √2. Again, the exact bound doesn't matter so much. You can read it if you like, but the important thing is it's better than Minkowski's bound. Again, we can define an analogous computational problem where I give you the basis and you give me a lattice vector, non-zero, which corresponds to Blichfeld's bound. So what exactly is the complexity of this Blichfeld problem? Well, we're able to show that it's in PMPP to the 2n. It reduces to finding a collision, a 2n-wise collision in a compressing function. And again, interestingly, we're able to show that there's a smooth trade-off. The more collisions you can find, the shorter the lattice vector you can find. And finally, we move on to some structural results about these complexity classes. We have these very general complexity classes which form a hierarchy, and we'd like to understand when exactly this hierarchy collapses and when it doesn't. First, we're able to use the well-known Merkle-Damgard construction and a more recent construction of list recoverable codes from BKP 18 to show inclusions for these complexity classes for particular parameters. Then we show some very weak black box separations. These are meant to give off a starting point for showing more advanced separations between these classes. We should note at this point that concurrent work of Jane, Lee, Robera, and June defined the exact same multi-collision TFNP hierarchy that we have defined. And they showed a full black box separation, essentially, between PMPPK and PMPPK plus 1, which shows that there is no black box reduction that lets you find a k-wise collision, k plus 1-wise collision in a compressing function from finding a k-wise collision in a compressing function. And here's an image from their paper. What we call PMPPK, they call KPPP. And we have this hierarchy along the middle here, and they basically show a separation along every step of this hierarchy. They also show that this hierarchy is related to other TFNP subclasses. This work has shown that there's no black box reduction. However, interestingly, there's a non-black box construction that one can construct collision-resistant hash functions from multi-collision-resistant hash functions. So we're left in this strange area where we know that there's no black box reduction, but we're still able to give a non-black box reduction. And we say some things about this in our work as well. And finally, I'll leave you with some open problems. The problem that excites me most is where exactly we should put the MRR-W bound. The MRR-W bound is the best rate-distance trade-off for codes that's known. It's rather advanced and proved using Fourier analysis, and therefore it seems hard to put it into PMPP, which is characterized by a multi-collision pigeonhole principle. Similarly, the Kabatsiansky-Levenstein bound for lattices is proved using Fourier analysis. It's the best bound for lattices that's known, and there doesn't seem to be a nice combinatorial proof out there. So we ask, can you put it in PMPP, or is there some other natural TFNP subclass where this bound belongs. We should also note that our PWPP hardness results for that grid I showed you are only for codes specified by circuits, where the code is the image of some polynomially sized circuit. Do these hardness results extend to linear codes? This would be quite a surprising result because it would show that finding short code words in a linear code is sufficient to break any collision-resistant hash function and would have quite significant impact on cryptography. And finally, we'd just like an understanding of this hierarchy that we've defined. What exactly is the relationship between these parameters A, B, and L? When do they collapse? When are they black box separable? And when are they just completely separate? Thank you.